page or the screen Middle-earth offers enormous opportunity for analysis. In this video we'll be taking a look at a few moments from an unexpected journey and analysing them mathematically, so let's see what we can find. Here in the prologue we get our first glimpse of a black arrow in flight. Let's determine its velocity. First we need a scale against which we can make actual measurements, and for this we can use the black arrow itself. Weta lists their replica as being nearly 2 meters long, and this is consistent with what we see on screen. What we want is a plot of the arrow's displacement with time, and this can be done using the free software tracker. We set up the scale using the calibration stick, aligning it with the ends of the arrow. And then we set up an axis on which we will be measuring. Now we track the position of the end of the arrow in each frame. This gives us data points we can plot in Excel. The rate of change, or the gradient of the trend line, is our velocity. It is only about 14 meters per second. This is really quite slow for an arrow, being slightly slower than this one shot from a very low powered bow, and a good deal slower than really functional weapons. In fact, assuming negligible air resistance and normal Earth gravity, the black arrow in this shot ought to only rise by about 2 meters and follow this trajectory. We calculate this by first breaking the velocity into its horizontal and vertical components. No forces act in the horizontal direction, so the displacement is simply the velocity multiplied by time. In the vertical direction, we need to account for the downward acceleration due to gravity. The peak of the arrow's flight occurs at its turning point, when the vertical velocity, given by the derivative of the displacement equation, is momentarily zero. So the arrow is definitely too slow to fly like it does in this shot. It's difficult to estimate the height of the arrow at this point, but we do know that in film time the collision occurs 1.46 seconds after the launch of the arrow. We can also see that the arrow is almost at its turning point by the time it hits the dragon, so with this assumption, the time and the launch angle, we can estimate a more appropriate launch velocity, and this we find is 31 meters per second, giving this trajectory, which is somewhat more compatible with the shot. At this speed, the launch of the arrow would look more like this. Another interesting measurement to make would be to compare the heights of hobbits and dwarves with the human-sized characters. This actually proves difficult because we need a shot where two characters are entirely in frame, standing side by side and at the same distance from the camera. Shots more or less like this happen occasionally, so we can make our measurements and average the result. What we find after 7 measurements is that the hobbit-scale characters appear on screen about 3/4 the height of the actor, making Bilbo, for example, about 1.3 meters or over 4 feet tall. Incidentally, this is quite tall for hobbits, as Tolkien describes them. This film is often criticised for how fast Radagast the Brown apparently crosses the Misty Mountains, travelling from Dol Guldur to the east to the Trollshaws to the west. To investigate this, we first need to know the distance between these locations, and for this we have this map. The direct distance is about 530 kilometres, but a more reasonable path might be closer to 780. Through video analysis, I estimate the speed of Radagast's rabbit sled to be about 15 meters per second while he's being chased by wargs. If this is accurate, the distance could be travelled in just 14 hours. Of course, the actual crossing of the mountains would add a great deal of time and the rabbits would need resting. So how much time does the film allow? It really seems ambiguous. In one scene Gandalf mentions Radagast and we cut to the scene in Roscommon. In the next scene the company arrive at the Trollshaws and it's the next morning that he arrives, but there's no reason to believe that there isn't at least a few days in between these cuts. Now let's take a look at the company's entrance to Goblin Town. This shot has a camera move, so we need to move the axis and the scale to account for this. Tracking the first dwarf and plotting the horizontal and vertical displacements, we get a linear and a parabolic plot. From this we estimate a downward acceleration of 13 meters per second squared, which is close enough to the expected 9.8 meters per second squared given our measurement uncertainty. We can also find that the velocity as they exit the tunnel is about 3 meters per second, and that after falling 4.5 meters they hit the ground at 11 meters per second. In this shot, the time between when Bilbo releases the rope and when we hear the collision sound is 3.3 seconds. If he were free falling for this time, the drop would be about 53 meters and he would land with a speed of 32 meters per second, if his initial velocity was 0. He does have some velocity sliding off the rope though, so the actual distance is likely to be greater, unless he is slowed by sliding against the walls of the cave, as may indeed be the case. Using the work energy principle and measuring the depth of the cushioning mushrooms, we obtain an average impact force of 51,000 newtons. But survivability really depends more on impact time, and we see that if the impact time was just half a second, Bilbo would experience about 7 Gs, which is technically survivable. And finally, let's look at this shot. We see that the base of the Lonely Mountain is just on the horizon. We can measure from the map that the Lonely Mountain is 380 kilometres from where the company stands on the Carrock, so ought it appear on the horizon? Well, the distance to the horizon primarily depends on your height above sea level and the diameter of the Earth, given by this equation, assuming a perfectly spherical Earth and no atmospheric effects. Putting the known distance into the equation, we can find that in order to see the mountain on the horizon, the peak of the Carrock would have to be nearly 12 kilometres above sea level, which is pretty clearly not the case. And this is where we end. Thanks for watching.